Thank you, everyone. It's such a pleasure to be here today. My name is Shichin Li. I'm from the Boston Consulting Group. I'm primarily working within our tech practice area. And it's very exciting. We have a very diverse and deep experts in this panel today. I will first just give the floor to maybe let the panelists introduce yourself a little bit. What's your name, which organization you're coming from, and what is your area of focus, area of expertise. And then we did prepare a few questions, and we can go from there. Maybe let's start with Sean.
Hey guys, Sean Jump with C Partners Consulting, French-based global management consulting firm. I've worked in the energy sector for the last 21 years, and what I do is I help clients find the intersection of theoretical value from emerging technologies with use cases that help them identify value. I'm a consultant, so I use the word optimization a lot, but theoretically, the word optimization is coming from a huge background of things. And now it's really exciting to see companies like Pasqal and others bringing these solutions to market where you can actually start implementing them, especially in the energy sector across a number of different areas. And so that's where I focus my time, my effort, and my attention.
Awesome. Rana?
Ray Gomez. I lead sales and biz dev for the quantum computing platform at NVIDIA. I've been in industry for around 11 years. About 3/4 of that I spent in the energy side of things, and then about 2 years ago, I saw that NVIDIA was investing heavily in quantum computing, that it was a field that our CEO, Jensen Huang, cared very deeply about, and that nobody was leading it from a sales perspective. So I raised my hand. I wanted to get back to my physics roots, and I've been working in quantum computing for the last 2 years. It's a very exciting field. I love working in it. I kind of feel like this is what it must have felt like to work in nuclear physics in the 20s and 30s, where we're figuring this field out as we go. There are new discoveries that are happening all the time, and 30, 40 years from now, I can see a really interesting Oppenheimer-like movie coming out about the field of quantum computing, and I love being able to work with the people who are probably going to be in that Oppenheimer-like movie. So, nice to meet you.
Awesome, thank you. Davide?
Hi, I'm Davide Venturelli. I'm Associate Director of USRA, which is an organization that since 1969 works with NASA on academic research. And in that capacity, I lead a team of about 10 people at NASA Ames Research Center, Quantum Artificial Intelligence Laboratory in California. And we work for the space agency on applied quantum computing with a variety of techniques. And I really resonate with what Christophe was saying about co-design. This is a moment where we're not having any plug and play system. We know that the system 5 years from now will be very different from the systems we have today in terms of hardware. So we really need the deep physics expertise and to tag alongside basic science efforts in order to understand impact for applications ultimately. And I do work a lot with the DOE and DARPA and other US government organizations. And NASA, I think, that has an applied view, an application view, a power user view, which is unique. And I'm very glad that now the conversation has been shifting a little bit from basic functionalities to impact of quantum computing.
Awesome. And then move on to Professor.
Yeah. Hi, everyone. I'm Tirthat Patel. I'm an assistant professor at Rice University. And my research is actually in the applied aspect of quantum computing as well. So I work on the systems side, so what you would call operating systems and architecture level of quantum computing, mostly focusing on hardware-software co-design and trying to compile applications so that they can run on the hardware that we have right now and the hardware of the future. So we focus on problems such as how do we minimize the size of the algorithms, how do we customize quantum machine learning tasks so that we can run on different types of hardware, including neutral atoms and superconducting, and different types of hardware technologies. And I actually joined Rice just last year as part of the Rice Quantum Initiative, which is a massive initiative at Rice related to hiring multiple faculty and developing workforce in the quantum area, not just quantum computing, but quantum sensing, materials, communication, quantum simulation, different aspects of quantum computing to really get the ball rolling here in the Houston area. Yeah.
Awesome. I actually want to start with Professor Patel. So you are at the most sort of leading edge quantum research, and you see the latest, greatest research trends from a laboratory environment. I was curious to see from your perspective, what are the sort of the latest trends or perspective, and also what are some major gaps that you see in quantum computing field that is needs, to be filled?
Yeah, I mean, a few innovations have come about recently in the last few months. I think actually Christoph mentioned a few of them specifically related to quantum error correction. There have been some big innovations related to implementation of logical quantum qubits. There are still gaps related to how we can go from there to scale that technology forward. Another gap, I would say, is focusing on different aspects of quantum computing in terms of the metrics that we judge it by, especially in this near-term era. So typically, the metric that gets focused on is speed. But we're also in our group looking into other metrics like resiliency, energy efficiency, cost efficiency. My background also comes from supercomputing infrastructure. So I know the operations and maintenance costs related to those. And quantum computing can really help with those aspects as well. So I think getting a more holistic picture of the other metrics that we can focus on, especially in this near-term era where we can run applications that may not be able to achieve the level of speed up that we would in the future, but they would still help with these other metrics that we can focus on.
Awesome, Ray. I see you nodding your head a lot when Professor Patel was speaking. I was wondering, do you echo his perspective, especially from a commercial standpoint? Do you hear the similar thing from your clients? And is this, for example, do they primarily only focus on the speed, or are there any other aspects?
I think one aspect that needs a lot more focus is on expanding the field of quantum computing from physicists to other domain experts. Right now, a lot of quantum computing is done essentially at the assembly level language, where people are programming individual gates and rotations, and that's great. But we need to build an abstraction layer that opens up the field of quantum computing to domain experts like computational chemists, for example. We were working with a pretty large pharmaceutical company who's got a sharp quantum computing team. We were trying to develop some application for molecular docking to simulate molecular docking. It was going to be this hybrid quantum classical approach. And after a while, we really hit this wall on, where is this POC going, because they have a really strong understanding of the quantum computing aspect. NVIDIA, we brought that hybrid aspect in the traditional HPC, and our software platform lets them kind of bridge the two together. But it wasn't until we got the computational chemistry team involved from this pharmaceutical company where things really started to click and take off, because then we weren't sitting there trying to wonder, okay, well, what molecule would we apply this to? How many qubits, how many gates are we going to need in order to really make a difference? We brought the computational chemistry team in. We said, if we could do this POC and brought you in and showed you how to use these tools, what is the smallest molecule that would move the needle for you? And once they were able to kind of bring that perspective in, get their hands dirty with the tools, understand how they could leverage quantum computing for the field of computational chemistry, that's really where the magic started to happen. And that's when we quickly rose up and got C-level engagement and visibility on this project. So I think moving quantum computing out of the domain of pure physicists to the domain scientists is something that needs a lot more focus.
Awesome. I actually want to move on to Davide. So we heard a little bit about quantum computing use cases in energy this morning. And when we think about quantum computing, two words immediately jump to my mind. One is simulation. Another one is optimization. I'm curious, based on your experience, what are some emerging use cases that you see in space exploration, and just based on your experience?
Yes. So at the moment, all activities we are doing and targeting are substantially inspired by applications. Okay, they're not really directly impactful. Even if they could be, we take an approach which is very science-first approach. And this is all across the government. The entire National Quantum Initiative has invested in 5 centers hosted DOE labs. Our team is active at Brookhaven and at Fermilab. And each center has missions. And we're all very much into trying to understand progressively things and understand the signatures of quantum advantage for applications. This said, I am super excited about the applications in quantum machine learning, and there's a story which is storming in NASA corridors today. Like, if you look at the NVIDIAs and the Caltechs and the Googles and the of the world that have deployed generative AI machine learning, physics-informed machine learning, especially neural operators kind of stuff, they revolutionized weather prediction overnight, okay? Right now, what NASA was able to do in I don't know, like weeks, now it's going to be done in seconds, okay? Because people have co-designed with a lot of trial and error neural networks that are able to learn models which are super difficult to integrate otherwise. Now, knowing quantum mechanics, knowing quantum machine learning, if we have systems such as analog, thousands of atoms, programmable, coherent system that can act as quantum neural network, and we have the availability to shape them and design systems, hybrid machine learning systems that exploits quantum mechanics. We have a playground which is unprecedented. It can be as minimum as good as the classical one. Let's call it that way, right? So I'm very excited about this empirical phase of quantum computing where, thanks to the deployment of moderate to large scale systems, they don't need to be error corrected. They need to be reliable, coherent, well engineered, at a scale where we cannot simulate them otherwise. We can try to impact partial differential equation solving, time series forecasting, spatiotemporal dynamics simulations, and those can be used for all sorts of space applications, from nuclear reactor design to climate predictions and models of, for example, one project I have right now, which is also in collaboration with Pasqal, is on tropical cyclone tracking as well. It's just a use-inspired. Is actually, how do we simulate a chaotic system with a quantum machine learning method? So those things are very exciting to me. And unfortunately, there's not going to be a theorem that somebody comes up mathematically tomorrow in some university telling us that this is going to work. Because in the real world, that doesn't happen. What's going to happen is people will discover by serendipity and by trial and error designs of quantum heuristics that actually work in practice. And this is in optimization, in machine learning. And that is where I really hold my hope and my career.
Yeah.
So, yeah. Can I just add to that? I thought that was a great example of using quantum for AI. But like the previous speaker said, there's another side of that coin, which is using AI for quantum, which is another really exciting field. And I just want to talk briefly about some work that we did with Ilan Osperu-Guzik from the University of Toronto and St. Jude's Children's Research Hospital. Ilan, if you don't know him, he is one of the original developers of the variational quantum eigensolver, VQE. It's kind of been one of the most dominant quantum algorithms of the last couple of years. And we worked with him and St. Jude's Children's Research Hospital on applying AI to quantum computing. And we took a large language model, I believe it was GPT-2, and trained it on the field of quantum computing, but then also on chemistry simulation, and used it to create what he calls GQE, the generative quantum eigensolver. And we now have this large language model that is able to create quantum circuits with desirable properties much faster and more efficiently than we would be able to do it by hand. And so it's just a really exciting example of now we're using AI and large language models to make the field of quantum computing better. And it's open source. You can read the archive paper. If you just look up Ilan Osperu-Guzik, GQE, you should find the archive paper. And we're working at NVIDIA to build tools and to kind of open source it so that way it's more easily accessible to people.
That's awesome. I want to move to Sean, and I know you work at the intersection between energy and quantum computing, and then we heard a lot of very compelling use cases and applications this morning. So curious to hear from you, based on your experience, what are some specific applications and use cases that you have seen, either from your clients or from your industry, that you have seen have compelling ROI and compelling value proposition?
Yeah, so for me, it all comes back to kind of an acronym, IML. So it's infrastructure, materials, and logistics. Those are the three areas that pop up across most industries where you can find value. And so, like I said before, there's a lot of ways that you can find optimization. You know, first came machine learning. Now we're entering the stage of kind of artificial intelligence, and now quantum. Quantum is going to take something that would traditionally take, 1,000 years on a normal computer, mere seconds. And so when you start to apply that to things like surgery room booking systems, the right doctor, the right room, the right patient, the right tools and techniques, and the right assistance, you can make miles and miles of gains above where you were before, especially when hospitals were divided to COVID units and traditional hospitals. It became more complex. When you look at things like infrastructure, you look at what's going on in Sweetwater, Texas, loads and loads of generation capacity between solar farms, wind farms, and how do you take all of that generation capacity and connect it to the rest of the grid and make sure that you're using that energy in an optimal way. If you look at materials science, the way that they even constructed the COVID vaccine happened so much faster because they were able to apply qubit logic in order to test and validate things much faster than they've ever been able to before. And when you look at infrastructure management, with what Wasik was saying earlier, the demurrage for a marine vessel to just sit offshore is tremendous, especially when you operate at the scale of ExxonMobil, Chevron, Shell. You're spending millions, if not billions of dollars a year just waiting for ships to come into port, or just waiting for a tank to run dry so you can batch it with the next one, or waiting for a pipeline to clear. These things are what people are trying to solve every day in every way. I've created a persona for this guy. I was telling Ronaldo about this earlier. Sam the scheduler. He wakes up at 5 a.m., drinks a pot of coffee. He's got Post-it notes all over his office. And he is the neural network trying to decide what products should go through what pipeline and load what marine vessel day in and day out. And he can operate pretty smoothly and cleanly as long as there's no disruptions. But as soon as something goes wrong, if there's a boat that's delayed, if there's a pipeline batching that didn't happen the right way, if there's a blending operation that didn't go as planned, what do you do next? Everybody picks up the phone and calls Sam. And so what happens now, Sam can leverage real-time quantum computing to actually look at what scenarios would look like across a number of different variables. How do you optimize profitability? How do you optimize delays in order to dodge SLAs for important customers? How do you do manufacturing in a similar way? It just spans across so many different use cases. And I like to think of it as a little bit of what everybody on the panel said today, which is how do you take it from the theoretical world and make it actually used? And I constantly think of this story that I was told as a kid called the story of the potter, right? You take two people, one of them is tasked with creating the most beautiful pot in the world. The other is tasked with making the most pots in the world. Say, get started, come back in a month, and let's see the results. The person that was tasked with designing the nicest pot spent all of his time making these beautiful sketches and drawings and theoretical ideas of what the pot should look like, and he made one and it looked like crap. The other guy made a bunch of pots. Every time he made the pot, he got gradually better. So at the end of the story, the guy not only made the most pots, but he also made the most beautiful pots. And so it's a parable to say, the more we use it in practice, the more people get exposed and educated about what quantum is, the more you're going to see practical use cases emerge. And so echoing what everybody on the panel has already said today, taking it out of the theoretical space, applying it to scientists that know how to use it in the physical space is going to be the best way to move things forward.
Absolutely. I think this is actually a pretty good segue to my next question. I think this is a very meaningful one, especially given how diverse our panel today is. We have academia, we have government agency, and enterprise, and also professional services, which is the importance of a local ecosystem, right? So what's your perspective on how the role of the local ecosystem play in terms of progression of emerging technology, like quantum and AI and others? So what different parts of the ecosystem needs to do in order to work towards the collective goal? Maybe we can start from Professor Patel again?
Yeah, absolutely. I mean, as everyone on the panel said, to get it from theory to practice, we do need to be able to collaborate with our local system. And Rice University has very strong collaborations with the Texas Medical Center, which is right next door to the Rice University campus, and also the energy sector here in the Houston. We actually have two separate institutes that are dedicated towards these collaborations. One is the Ken Kennedy Institute, which focuses on AI, data, and computing. And more recently, one of its cluster actually focuses on quantum AI. So seeing how quantum computing and quantum machine learning can benefit different applications of AI in the energy sector and the healthcare sector, specifically within the Houston area. Other institute is the Smalley Curl Institute, which focuses on a lot of different technologies, but one of it is quantum computing technology. And that institute is also focused on developing local collaborations with these different agencies. I think if I can say something about the practice of it, it really is the ability to be able to understand the pain points of different application users, really understanding what are their needs, what are the gaps in that solution space, so that we can actually develop solutions for that. In my research specifically, we are actually focused on different quantum AI solutions, as I said, at the systems perspective. So we're looking at different data sets that we can get from these collaborators and perform tasks such as anomaly detection. Anomalies are very common in the energy sector, power grid failures. They're also very common in the healthcare sector. We're looking at how we can take these data sets and see if we can use the correlations on these quantum computers, especially analog quantum computers, to prepare the data, which will bring out these correlations, and we can identify these anomalies even faster. So these kind of collaborations within the local ecosystem are extremely important to RISE.
Great. And how about from NASA?
Well, one of my favorite quotes is, business happens at the speed of trust. I think that to build trust between entities, a local ecosystem is an incredible asset. I've been living in Silicon Valley, I lived there like 10 years, and I could really see the difference when I moved out, of an ecosystem which has been created for decades to generate innovation and something that actually doesn't have that. And so I do believe the catalysis, the ability to facilitate impact of a regional ecosystem is really, really important. And I think that though it's very important that doesn't become an echo chamber. It doesn't become, just a way to stay isolated. And it's very important that it has a global perspective, a global opening. I'm preaching here, but of course, Pasqal is a French company, so it's obvious that we all agree that international exposure it's key, especially in an endeavor such as quantum technologies, because the quantum technologies are really like a very noble, large-scale, humanity-scale challenge, like to harness the power of physics to process information and to get us to the limit of what we can do with the information. So very important, I believe, very important to work with the universities, because that's where a lot of the talent pipeline arrives, and very important to attract international talent as well, at least in this stage of the technology development.
Great.
I think having a strong regional ecosystem is absolutely critical to making quantum computing a success, because it's such a resource-intensive field. You need the people who are working on the quantum hardware supply chain. You need the quantum hardware vendors, the QPU vendors. You need academia. You need software application people. You also need enterprise companies who are willing to invest and test out quantum computing. And to have all of those in one region is not very common. And I think one of the most exciting regional hubs is actually what's happening in Denver, Colorado with Elevate Quantum, where they just were awarded the EDA Tech Hub grant. What they're trying to do there is build an open access quantum lab where they've got academia from the School of Mines at CU Boulder. They've got one of the highest concentration of quantum startups and companies, from the suppliers, the dilution fridges, the actual QPU vendors. They've got a high concentration of enterprise customers, and what they're building there, what their goal is to accelerate the innovation loop on both the quantum software and the quantum hardware side. they're putting an NVIDIA supercomputer on site so that way they can accelerate not only the design of quantum algorithms and applications, but we can also accelerate the underlying physics of what's happening inside of a QPU. So we're accelerating the design of QPUs. But then they're also building a quantum fab to accelerate the building and construction of QPUs themselves. They're putting in what they're calling a cold cloud, where they've got essentially dilution fridges as a service. And going back to the parable you mentioned, you've got to move fast and break things. In order to do that, you need a very strong regional ecosystem that has every single essential component all co-located together. You also need the facility so that way you can have your supercomputer co-located, tightly coupled to your QPU, and you need the ability to build QPUs and iterate on those designs as quickly as possible. And so what they're building at Elevate Quantum, I think, highlights the importance and hopefully the efficacy of having a high-density regional ecosystem.
And across different parts of the supply chain. Very interesting. How about you, Sean?
Yeah, I mean, look, so when you start to mention the word quantum, most people lose interest pretty quickly. They're like, sounds cool, what does it actually do? I mean, even the President of the United States writes speeches to address the nation on a 14-year-old level. And so it's hard to create a brand for quantum in a space where people might not understand theoretical physics or the application of theoretical physics. But I think creating a brand around quantum and identifying the use cases that it can be used for is going to be critical to getting people to adopt it. Even here in Houston, I mean, recently when we had Beryl, we had millions of people without power, and you start to ask the question, well, what happened? Okay, clearly quantum computing can't solve a tree falling on a power line. However, quantum computing can solve sending the right technician to the right power line with the right tools and the right experience to make sure that that power gets restored in a meaningful amount of time, and then create a brand around that, right? Hey, CenterPoint Energy, let's not let that happen again. Let's solve this problem using quantum, and let's start getting people out to the right location at the right time. So grid infrastructure management is a great opportunity for quantum to create a brand for what they can do in the space. We also need larger energy companies to adopt quantum and start testing it and finding partnerships and ways to adopt it. It's going to be a very meaningful competitive advantage if people are willing to take a little bit of risk on the front end, break a couple of pots in order to find the one that's going to really work, and that's going to set the tone for the entire industry. Other industries are adopting technology in a more meaningful way. What's going to happen in the energy industry is they're a little bit bound by regulatory environment. They kind of wait a little bit to say, oh, okay, the regulation's been updated. Now I guess we got to do something. Case in point is the TCFD. It's a Task Force for Climate Change and Financial Disclosure. The SEC ratified this recently. It's tied up in lawsuits left and right by energy companies. Basically says any publicly traded company in the United States has to disclose Scope 1, Scope 2 greenhouse gases on their books. It's got to be audited by your consulting firm and validated. If you can't do that, they'll have a material finding, and your shareholders are probably going to be questioning your accounting practices. It's a huge deal. For banks and technology companies, not that big a deal. For asset-heavy companies like manufacturers, power utility, oil and gas, metals and mining, huge deal. So they're going to start to be scrutinized in different ways, and they're going to have to start to learn how to adopt technology, even if it's emerging technology, and start to play around with it and find ways that they can start to do things faster, better, more agile, more cleanly, and find materials, frankly, that can be used from the quantum space to develop things that will sink carbon, sequester carbon, and then add that into their supply chain so that they can improve operations.
Awesome. Thank you. Very, very insightful. I want to thank you all for your time today, and thank you all for your time, for your attention as well.